Hi, I'm Anders Hejlsberg, technical fellow at Microsoft, and I'm here to talk about TypeScript, which is a project that we've been working on for the last 2.5 years. So TypeScript is about solving a problem that we've increasingly heard from our customers. You know, in particularly over the last 5 years, customers and even internal teams keep telling us how hard it is to write large applications in JavaScript. Several reasons, you know, one being that JavaScript really was never designed to write large applications. It was sort of like originally intended for these 10-line event handlers, and now we're writing 10,000 or 100,000 line apps in it, and the language doesn't really have any large-scale application structuring concepts like classes or modules, and also it's entirely dynamically typed, which means there's no static type information off of which we can power intelligent tooling. And if you think about what it is that powers the intelligent IDEs that we all use today, it really is static type information that makes it possible to do code completion, safe refactorings, finding all references, go to definition, etc., etc. So 2.5 years ago, when we were thinking about where do we go next with JavaScript development tools, we thought it'd be really neat if we could strengthen JavaScript with those key concepts that are missing for large-scale development, like classes, modules, optional static typing, but to do so in a way that doesn't sacrifice the inherent thing that makes JavaScript so interesting, i.e. cross-platform, open standards web, and so forth. And that is what TypeScript is. It is a language for application scale JavaScript development. So it's a language for large or application scale JavaScript development. Next level down, or the more technical description is TypeScript is a superset of JavaScript that compiles to plain JavaScript. And it does so, the compiler itself and the code that it produces runs on any browser, any host, on any operating system. And the compiler and the associated language services and library typings and so forth are all open source. We put this project out in the open about 2 days ago. What I have here is basically, you know, the publicly available installation of it that we're going to try and play with. Now, so TypeScript starts with JavaScript. All JavaScript code is valid TypeScript code because we are a pure superset of JavaScript. And that means that you can just copy and paste JavaScript into a TypeScript file and then work with it there. It also means that TypeScript works with all of the existing frameworks and libraries that are available out there today, like Node.js or jQuery, Backbone, Underscore, Prototype, etc., etc. There are lots of them and new ones coming practically every day. So the thing that we then add on top is optional static typing, classes, and modules. And those are really sort of the things that allow us then to build great tooling because they're the missing things that power the IDEs today. The cool thing though is that there's zero cost. All of TypeScript is purely a development time tool. Once you compile, you're left with plain JavaScript, and there's no runtime component that needs to be present in order to run the generated code. In fact, we simply compile to idiomatic JavaScript, the JavaScript that you would have written if you wanted to emulate classes or modules. And the final code runs, as I said, in any browser, any host on any OS. So let's actually try to do a little bit of demoing and see what this looks like in action. Here is the TypeScript website. Well, actually, it's a local copy I have just in case we lost connectivity. But this is what it looks like. And we're going to go and play with TypeScript in the TypeScript Playground, which is basically a web page where you can type in TypeScript and see the compiled output in a window on the side. I'm going to switch here and grab my first little demo. And so here you see some JavaScript, and here you see the compiled output, which happens to be exactly the same because we are just a superset of JavaScript. Now, if you look at this code, there's something funny about this code, right? I mean, I'm like taking a parameter x, and I'm adding a property to or setting a property, but I'm also plussing it together. But hey, this is valid JavaScript. It just so happens to not be meaningful, but it's valid. Now, it would be nice, let's say, for example, that I knew that x was going to be a string. It sure would be nice if I could somehow indicate that. And, you know, it's not like we're inventing anything new in that sense. You know, for example, if you use a tool like Google's Closure, where you put type annotations in comments, there are tools that can check these things for you. But having your type system in comments is not particularly conducive to readability of the code, nor is it particularly expressive. You know, there are a bunch of things that you can't say in these comments, and you can't put them in all of the places that you would like to put them. So what TypeScript does instead is it allows you to put type annotations in your code. So I can say x is of type string. And when I do so, you see that our IDE starts to light up. I should mention that what is powering underneath this edit box that I'm typing in is the TypeScript compiler and the TypeScript language service, because TypeScript is written in TypeScript, and when you compile it, you get JavaScript, and you can just use that anywhere. And so that's what we're doing here. And so the first thing you see is that we get something here that says there's no name property on type string, which is true. There isn't. We also see, if we hover over v, that we've inferred that string plus string is a string, and therefore v is of type string. And we see that alert is a thing that takes a string and returns void, and therefore it is valid to pass v to it. Now, let me try to get rid of that line in error here, and let's try one of the other primitive types, number, for example. And now we see, now we're inferring that number plus number is a number, and now we're trying to pass a number to a method that expects a string, and that in turn is also an error. So here's some more, you know, static type checking happening. Let's try to use a bool instead. And now we see that operator plus can't be applied to bools. Well, it actually can in JavaScript. It just so happens that you don't get a meaningful result, right? And so, in a sense, what this is about is trying to siphon out that meaningful subset of Java, the semantic subset of JavaScript that makes sense. And that's basically what we're doing here, right? Now, we also allow more complicated types like arrays. For example, I can say that x is a string array, and now when I index into x and press dot, you see that we know that there are strings, and therefore we can show you all the methods that are available on string, and not just their names, but also their signatures. So we can see that care code at is a thing that takes an index, and which is number, and returns a number, and so forth. Other typical patterns that are interesting is we can say x is a function that takes no arguments and returns a string. And now when we call it and say dot, again, you see we get statement completion. But of course, one thing that's really interesting is having the ability to describe a shape of object. Here, for example, I'm saying that, that my function takes an x that is an object that has an A and a B property. And now when I say x dot, you see that we get statement completion here, x dot A, x dot B, and so forth. Now, I might also want to give a name to this structural type or this anonymous type. So you see you can write types just in line, but of course you can also name them. I think I have this little example here that shows you how you could write an interface thing with two properties in it. And that's really just interface here. Think of it more as I'm writing an object type whose name is thing, and it has two properties. And let me now try, for example, and say var n equals process of a colon 10 comma b colon hello, for example. Now, a couple of things worth noting here. First of all, if you've been following along over in the generated JavaScript, you see that the JavaScript we generate is really just the JavaScript that you type minus the type annotations and minus the type declarations. So all of that is there, you know, for validation and IDE tooling's sake, and then it just compiles away. Now, the other thing you'll note here, if we try to look a little bit at this program, so we've defined a to be a number, and here we return x.a, which means we've inferred that we return a number, which in turn means that we can infer that process is a function that takes a thing that returns a number, which in turn means that when we call process, we can infer that n is a number. And so you see how types flow through just a few annotations, and then we can flow it through the code once we know what's going on. Let me try to sort of show here what also happens. For example, let's say I add an extra property to my interface type here. Now you'll notice that I get errors here. It says process is missing one of the parameters. And I could fix that by adding my parameter C. But I could also instead indicate that C is an optional parameter. So this is a pattern that's very common in JavaScript, where you take, say, options bags that are a bunch of options, but you don't actually have to specify all of them, right? So here we're saying that A and B are mandatory, but C is optional. If I give a C, it must be a bool. If I give a C that isn't a bool, now it's an error. So we can sort of express some of the more intricate parts of what goes on in JavaScript. Let me actually try to take this piece of code here. I'm just going to copy it, and then let's switch to Visual Studio and just get ourselves an empty TypeScript file. So now, part of TypeScript, the distribution, is a plugin for Visual Studio that uses the compiler and language service to power up all of these intelligent facilities in the IDE. As I said, this stuff is all open source, so you can use it anywhere else. You saw an example of using it in a web browser. Someone could build an Eclipse plugin and do the same thing. I'm just going to paste it in here and then continue playing with our code in here. So one thing you, of course, can express, in types is methods. So now we're saying that thing has A and B properties of type number and a foo method. So now when I do statement completion, you see we have a foo, and when I do open curly, it tells me what the signature of that guy is, and so on. And again, here we can infer then that now we return a string because foo returns a string. We actually also allow you to express overloads. So I can say there's foo actually is a method that when you give it a string, returns a string, and when you give it a number, it returns a number. This happens very often in JavaScript. For example, like think of jQuery and the dollar object that has 7 different overloads that you can, if you give it a function, then it does this. If you give it a string, it does that. If you give it an object bag, it does this other thing, and so on. And so it's important to be able to model that in the type system so we can follow along, and when you say dot on that, give you the right type information again. So now, if we look here, if I say x.foo, you'll see that there are now 2 overloads. Oh, that should be an end. Yeah, anyway. So, and if I give it a number, here you go, then process now returns a number. Now, this stuff here actually is really the same as writing this. So foo, what I'm really saying here with these 2 overloads is that there's a foo property that has 2 possible call signatures. One that takes a string and returns a string, and one that takes a number and returns a number. But I can describe further things on my function. For example, it also has a data property. So, and this, again, is stuff that occurs. So now when I say foo dot, you'll see that there's a data property, but I can also call it with 2 different overloads, and so I can model all of these crazy things that occur in JavaScript libraries. In fact, just for completeness sake, let me add a couple more here. I could now also define that thing can be a constructor function that takes a string and returns elements, and when you index into it, you get dates and so forth. And now, so crazy stuff, when I say new x here, it says, oh, you must give me a string, and when you do, then I'm going to return an element, et cetera, et cetera. So we basically can model all of these things that go on in the JavaScript DOM, jQuery, all of the frameworks. Okay. Let me get rid of this stuff and try to paste in some other. Here's a little more advanced example of type inference, a function that closes over a local variable and returns an object with a bunch of function properties that use that local, and this is how you get privacy in JavaScript. It's a very, very common pattern, right? If you look in this piece of code, the only thing that differs from regular JavaScript is this one annotation here that says that this function takes a number. But we can infer all of the types from this. So if you hover over the return statement here, you'll see that we've inferred that this returns a thing that has 3 properties that are each of a function type that has certain argument types and so forth. And in turn, make accumulator, therefore, is a function taking no arguments that returns an object literal containing 3 functions that et cetera, et cetera, et cetera. So we can sort of grok it all. And now when I say var a equals make accumulator, and then a dot, you'll see that there's an add here, and that I need to pass a number 5 and so forth. Now, so this shows how we can infer from code that you're writing. But sometimes inference, you want inference to go in the other direction. You may, for example, have a declaration of an interface that you want to go implement, and now really you would like to make inferences from that about the code that you're writing. So let's say that my make accumulator function here is something that's supposed to return an accumulator, right? Well, you'll see that it all works out now because we actually have structural typing here. So the mere fact of writing an object literal that has the right shape is an implementation of that interface. You don't have to first declare that you implement it. But the other thing that's really cool is that if I made a mistake here, like typed in the wrong property name, then it tells me what's wrong here. It tells me that, hey, you're missing property add from accumulator. Now, this is where tooling gets really, really useful. Imagine that this was like a 500-line object literal, and trust me, I've seen lots of them in JavaScript code, and there's something wrong in there somewhere. How the hell do you figure that out, right? I mean, that's what tools are supposed to do for you, and that's what we do here. Okay. Another place where this kind of contextual typing is interesting is, well, actually, I should show here that even if I get rid of that type annotation, you'll note that we can still infer that value is a number because you've said that you're returning an accumulator. An accumulator has an add function that takes a number, and therefore we can relate that and still flow the types in the other direction, right? This turns out to be useful. For example, if I say document dot on mouse move here, which is one of the events you can handle, equals function of e, and then open curly e dot, and you'll note that we actually know what e is here. And the way we know it is because we know what document is. Document is the root document. Document has an on mouse move that takes a mouse event and returns any, and therefore we can push the type information into e as a mouse event, and therefore we can give you statement completion on e when you say dot. And so lots of inference going on. The cool thing is I can actually go to the definition of mouse move and look at what this thing is. And that jumps you into, in this particular case, a file called lib.d.ts. And this is 8,000 lines of TypeScript declarations that declare the entire structure of the DOM and the JavaScript runtime library. This is actually generated from the IDL files that are standardized, so we know it's correct. and the type information is actually available. It's just that JavaScript itself has no way of conveying this information to you other than at runtime when it's too late, right? So here we can see that mouse move is this thing that takes a mouse event, and we can actually navigate around and check out all of these things and then see what their shapes are. Now, the thing that's really neat about this is that we can provide this file just as an adjunct file on the side. And once you have that information, the tooling lights up. And we can do that for any JavaScript library out there. So we actually do that for Node.js, and we do it for jQuery in the TypeScript distribution. So just as an adjunct file, we can provide the missing information, right? And then light up the tooling based on that. And I think that is just super, super valuable. Okay. So let me, let's see, where did I want to go from here? Let me go back and just sort of summarize a little bit about the TypeScript thing here. So basically what TypeScript does is it formalizes JavaScript's type system and provides a static view of it. But we're not trying to invent a new type system. We're actually bending over backwards to stay true to what really is JavaScript's type system. You see that we do a lot of type inference and structural typing, and the reality is that when you're writing TypeScript code, you actually end up writing very few type annotations, and then we just flow from there. As I said, it works with existing JavaScript libraries. And for the type system geeks out there, this is not a provably type-safe type system, because JavaScript is not, in a sense, provably type-safe. Well, you first have to define what you really mean by that. But the point here is that it is not a type system for the traditional sakes of type systems like performance or like strict validation. Rather, it is a type system that helps you author code and that reflects, you know, the reality, if you will. But it is optional, and you don't have to use it, but when you do use it, the tooling can help you more. Okay, let me try to jump back and show you some of the other features that are available. I wanted to show classes and modules, and we'll go back to the playground because it's instructive to see the code that the compiler generates. So TypeScript supports classes, so I can declare class point, for example, here and say it has two fields. Sorry, my typing is not great. X:number and Y:number, like so. And you see that we generate the code that is sort of typical for writing classes, where you have a closure in which you have a constructor function that we then return out of the closure. And now I can say var p equals new point. And now we know that on P, there's an X and a Y, so we can give you statement completion. So you can say P.X equals 10, P.Y equals 20, and so on. Okay. Now, of course, it would be nice to be able to give the arguments to my point here, but if I do, I get an error because we haven't yet written a constructor. But we could go write one. Constructor of X:number, comma, Y:number. And in here, we can say this.x. And again, you see we get statement completion on this because we know where you're at, this.y equals y, and so forth. Now, this class syntax, by the way, is aligned with ECMAScript 6's current proposals for classes. So the class and module extensions that you see in TypeScript are actually, in a sense, a preview of what's coming in ECMAScript 6. But then on top of that, we have layered optional static typing, which is not part of what ECMAScript 6 is doing. So, of course, you can have methods in classes. So let's write a dist method here, and let's say in here we want to return mass dot. And again, here you see I get statement completion on all the stuff that's available in the standard runtime library. So I want to return this.x times this.x plus this.y times this.y. For example. Let's format that a little nicer. Okay, so one thing you see here is that instance variables go on this, but methods go on the prototype. And this is exactly how JavaScript or ECMAScript 6 is planning to do classes, and this is basically the typical pattern that people use them when they write prototype chains in JavaScript. We allow some other things in classes here. For example, I could declare static field, static origin equals new point of 0, 0, for example. And you'll note now that statics go on the constructor function object, methods go on the prototype, instance variables go on the instance, and so forth. And now we understand what this means, so when I say point dot, you see that I get an origin member on point. Okay. We also allow you to write private members, but with a twist. So I could say, for example, private color, oops, colon string, like so. And now down here, if I say this dot color equals red, you'll see that we generate the code, and you see that this statement completion on this shows the color member. But if I go down here and say p dot, you'll see that there's no color member on p because it's private. So we limit you to access only within the class if you declare things to be private. However, in the generated code, we simply just generate a normal member called color because there is no way of having private members in JavaScript, at least not currently. Once ECMAScript 6 rolls around with private names, we could target private names for this kind of code generation and perhaps do a better job, but right now we do the best we can. Okay, a couple of other neat features. We support what we call automatic properties. This pattern of declaring fields, taking constructor arguments with the same names as the properties, and then saying this dot blah equals blah is super, super common. So we have a nice shorthand for that where instead you can simply, on the constructor argument, say public here and public here. And then we automatically inject properties with those names and inject the code to initialize those properties. We also support another ECMAScript 6 feature, which is default argument values. So I could give these arguments default values just by saying equals something, and then we inject the correct code to check whether they're undefined and so on. And now, of course, the type system now knows that it is permissible to omit the arguments in the call, so we don't get a red squiggly on that. Okay, well, I should also show that we, of course, support inheritance for classes. Let's try to declare class point 3D extends point like this. And then let's just take a look at what happened in our generated code. So we still have our point class right here. And now we also have a point 3D. And you notice that the code gen for that is a little bit different. We generate a function closure that takes the base class as an argument. And then we call a helper extends that sets up the prototype chain the way you're supposed to do in JavaScript. This is why classes are hard in JavaScript, because you're supposed to do all of these crazy things, right? This extends method is injected into the generated source code only if there are derived classes in that file. And that is the only time we inject code that you didn't write into the output file. Otherwise, the code you get is simply the method bodies that you wrote. So there is no runtime library or new collection classes or blah, 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 or anything associated with TypeScript. It is simply just JavaScript. Okay, I could, in here, write myself a constructor that takes x colon number, comma y colon number, comma, say, public, add an extra property z colon number, like that. And then in here, say, call super of x comma y, for example. And now you see that we generate the appropriate code for making a call to the super constructor, et cetera, et cetera. Yeah, so that's classes. What I wanted to show next is modules. Let's try to, actually, let me try and grab a little snippet of code over here. What I wanted to show before that, in fact, is arrow functions. So let me go to the toolbox and let me grab tracker. Here we go. Okay. And let me paste that in here. Okay. Here's a little piece of code. Scroll this up so you can see what's going on. Here's a little class that declares a counter instance variable, and then it has a start method, and in the start method we capture the onMouseMove event and have a little handler that increments our counter and does a console.log of the counter. So let's try and run it so you can actually run the output here in the playground. Let's bring up the F12 tools and go to the console window. And then we see that, there's something wrong with our code. We're getting a bunch of nans out of this. If we go back and look at what's going on here, the problem that we have here, and if I had actually been typing this code in, we would have already seen what the problem was. But if we hover over this now, you can see that this is of type any, meaning that we do not know the type of this here, and therefore we wouldn't have gotten statement completion to show count and so forth. But the reason it's a problem, or the reason this is of type any, is that you never know what this you're going to get in a function call, and sometimes you're going to get the wrong this. For example, in a mouse move event, you get the element that the move occurred on. You don't get the this of the surrounding context. Now, everyone's gotten bit by this problem, and people have gotten bit enough by it that there's a proposal in ECMAScript 6 to support what's called arrow functions, or what we in C# call lambda functions. So I could instead write this code as e-arrow, and then in a lambda function, this is always of the type of the surrounding context, or it's lexically scoped, meaning that I get the this of the outer function. And the way we code generate that is we do the nasty little thing that you normally have to do, where you say var that equals this and then that dot inside your function or whatever. We can simply code generate that for you instead here. What's interesting about it, okay, and let's actually just sort of run and prove to ourselves that that it now works. Yep, we're seeing what we're supposed to see. Thing that's interesting too is if in my little mouse move here, let's say that I did not refer to the outer this, then you'll note that we don't generate that closure. So we only inject it if you actually do it, and then we rewrite it to underbar this instead. Okay. Now, the other thing we support in TypeScript is modules. Let's say I wanted to put this class in a module. I could write here module, open curly. Down here, close curly. Oops. Of course, we want to give this module a name. We'll call it module utils. And you'll see that what we generate for a module, again, is a function closure, where we then, for all of the things that you export out of the module, if I say export class tracker, we then create a property on the module object for each of the exported items in there. So this is also a very, very typical pattern in JavaScript. And now, of course, we get red squigglies here because there is no tracker in the global scope. It is now utils dot, and if I say dot, you see that there's a tracker in there, and that's the one that we want, right? I can actually go deep with these things. acme.core.utils, and you see we just nest function closures sort of off the screen there. And now I have to refer to it as acme.core.utils. But you'll note that we do track it in the type system, so we know that the name of this type is acme.core.utils. In fact, we even allow you to import modules, so I can say import ACU equals acme.core.utils, for example. And then here I can use the shorthand for that ACU. And if you look down here, you'll see that what we've generated is just a variable that grabs that module object, and then you use that to reference instead. These modules we call internal modules, and they're very typical, like jQuery, for example, is an example of a module called $, right, that has a whole bunch of stuff in it. There's another kind of modules that are in common use out there called common JS modules, and Node.js uses those. And those are basically like source files that get loaded dynamically at runtime and have the ability to state their requirements in terms of other modules and state their exports in terms of an exports object. And we support those, so let me actually try to close down the playground here. And then let's go back in Visual Studio. And let's try to open up a server.ts here. And let me try to write a little 2-module node server application. So first thing I'm going to do is I'm going to import or reference the static typing of node.js, which is in a declaration file called node.d.ts. And I simply place a reference in my source file which tells the compiler that when you compile this file, also include that other file in the compilation. And now I can say import HTTP equals module of HTTP, which is one of the modules defined by Node. And in fact, if I go to definition on this guy, you'll see that it jumps me into the adjunct static type information file for HTTP, and this is what it is itself powering off of in order to give me statement completion help. Okay, so let me now try to write a function here, export function simple server that takes a port colon number, comma, message, colon string, like so. And in here, let's say we want to call http.createServer, and you see we get statement completion on Node here. CreateServer, in turn, is a thing that takes a callback function that has two parameters, request and response, so I can give those guys. And then in here, I can write the body of my code. Now, I'm going to just paste in some stuff here so you don't have to watch me type it all. But note one thing, that when I type result dot, we actually get statement completion on that. So we flowed the types from the declaration of create server into the callback function because we know what the types of those callback arguments are, and so we can flow it all without you having to explicitly state it anywhere. Okay, let's just go back here and say dot listen of 1337. No, sorry, a port, which was the argument that we got passed. Okay, so that's the first module of our little server. Let me create another. Let's see here, recent files. Let me get hello, this guy here. Open another empty file, and now let's create a module that uses the module that we just wrote. So I'm gonna say import server. Oops. Server equals module of server. And now I actually have referenced the module that I just wrote. And so if I say server dot, now I actually get statement completion on the module that I just wrote. So I can now call simple server, and it tells me you got to pass me a port number. So 1337, comma, hello, go to, for example. And then let's just also just say console dot log of listening, like so. There, and let's save that guy. All right, and now let me jump out and actually use the command line compiler. So we'll switch to Node, demo, and Node. And in here, you'll see now that we have our three files, the Node declaration file and the two TypeScript files that I wrote. Now I can simply tell it to compile hello.ts. I don't even have to tell it about server.ts because the compiler will automatically trace all of my imports and all of the references that I have and find the entire graph of files that need to be compiled and then compile those. So if we look at the output that got generated, we now have two files, hello.js and or server.js. We could just sort of take a look. Here's server.js. If we, oops. Try and take a look at that, and you'll see that the code that's in there is the code that I wrote with my import changed into a require. And if we type hello.js, you'll see again, it's pretty much the same code, right? Let's try to run Node on this server. So Node hello, and it's listening. And now let's go to, whoops, let's get rid of this guy there, and then let's go to localhost 1337. There, and we should see hello, go to. There we go. Yep. Okay, so that's a little bit about classes and modules. I could just quickly summarize here that basically, you know, these are the things that allow us to do scalable app development, right? And this is how you get to write really large applications and have tools that understand what the contracts are between different modules and have them enforced so you find the errors before you run your app instead of whilst you're running it. We're aligned with the emerging standards, so as I said earlier, classes, modules, arrow functions are all things that are proposed for ECMAScript 6 that we're taking inspiration from. And we support the two popular module systems that are out there, CommonJS, which is used by Node.js, and then AMD modules, which probably the most common loader there is require.js. And that's used for asynchronous module loading in a browser, and we support both of those. Okay, last thing I wanted to show was just a few larger applications, because we've been doing a bunch of little stuff here. So let's try to load up some of our samples. First thing I'm going to open is, let's see, demo/image board. This is one of the samples that we include, and let's just load up app.ts. So this is a multi-module Node.js application that uses MongoDB and the Express framework. So in here, you see that we import modules from various places. HTTP and URL come from Node. DB is actually a module that we wrote. We can navigate in and look at it. And in here you see that that in turn uses MongoDB, so we can navigate into that and check out the static typing of MongoDB. In here you see that we create a server, create a connection to it, and then just for convenience, we've defined some interface types that represent the entities that we're storing in the database, because they're all of the same type, and it's really actually convenient to have statement completion and validation on these entities that we're putting the right thing into the database. And then we've also written some helper functions like getUser here that takes an ID and then asynchronously calls you back when it's fetched the user from the database. And here you see we use the interface files that we just declared. Now, we can use the IDE to navigate in this larger app. We can, for example, find all references of getUser, and you'll see that here's the declaration of it. And then there are two references over in the app. Here's one that I think is interesting. If you look at this function here, there are 0 type annotations in this function, yet we know all the secrets about it. Because app elsewhere is typed as being of type express server, we know that express server has a get method that has a bunch of overloads, and one of them is one that takes a function that returns that has 2 arguments, request and response, and so we can infer what their types are. We know what the type of user is, the one that we declared over in the database module. And so when we're in here, if I say request dot, you see that I get statement completion. If I say user dot, you see that I get statement completion. So we know all of this stuff without having you to state it over and over. It's inferred from the code. Now, in the interest of time, I'm not going to actually run this one. I'm going to try and switch and show you another little sample, which is one called Warship. And let's try to load that guy up here, and let's get rid of this dude. No, and this dude. Here. This is a little app a browser app that uses jQuery and jQuery UI. And you'll see that we referenced the typing for jQuery and for jQuery UI. And let me show you how this works then, because the pattern between these two libraries is that jQuery UI is a library that builds on top of jQuery. It actually sort of monkey patches into the dollar object and adds additional properties that are for UI manipulation. So if we look at dollar, well, first of all, you'll see that we now have type information for jQuery. So we know the 7 overloads of dollar. We're going to pick the one that takes a string, and then we're going to press dot on it, and here you see all of the things that you can say on dollar. Now, this is the stuff that saves you from having the cheat sheet next to you or looking up in some HTML documentation, right? This is what tools are supposed to do for you. If we pick add class, then we can actually go to the definition of that guy, and you see now we jump into the jQuery declaration file, and you see here's the main interface for jQuery, and it has an add class. In fact, it has 2 overloads of add class. Now, if we go back, let's say we pick one of the ones from jQuery UI, like draggable, for example, and let's say we go to definition on that guy, you'll note that we jump into a different file that declares the same interface. So in TypeScript, interfaces are open-ended, and multiple files can contribute to the same interface. And that's how we model this notion that one module does something, and then another module builds on that first module by adding things to its types. And so we can model that in the type system, and that's just super useful. Okay, last thing I wanted to show is a really large project. The TypeScript compiler itself. Let me try to load that up here, and we'll just pick one of the files out of the compiler. The compiler is about 26,000 lines of TypeScript code. Here I loaded up the file that contains the abstract syntax tree class definitions. And as I said, all of this is open source, so it's stuff that you can just grab and look at. We can navigate in here, for example, go to the definition of the case statement class, which is a class that extends statement and so forth. And so I can navigate around the entire compiler. Now, you saw that at the top of this file, I reference a file called TypeScript.ts. If we go to the Solution Explorer in Visual Studio, you see that we've actually inferred the entire project that I'm working on here from those references. Because if we go to TypeScript.ts, you'll see that that in turn references a whole bunch of other files, and through these references the compiler can get the full picture, and it almost doesn't matter which file you open. We know the context, and therefore we can provide you all of the appropriate information. So in here, this is the main file for the TypeScript compiler. There's a class called TypeScript compiler, not surprising. TypeScript compiler instantiates a parser. We can go to the definition of the parser. The parser, in turn, instantiates a scanner. We can go to the definition of that guy. And so you can sort of navigate around very easily and see how the compiler is built. What I wanted to show, though, is one of the really neat things that you can do once you have static type information, and that's things like refactorings. And one of the refactorings we support is rename, for example. Let's say that here in the scanner, I have a field called line number that I forgot to rename that back to line from the last demo I gave. Anyway, there's a field called line number. If I look at all the places that this guy is referenced, if I do go to definition on this guy, go to find all references on this guy, you'll see that there are a bunch of references in the scanner itself, and then there are some over in the parser that we can look at. And here's one, for example, in the parser where we reference line. Now, up here, there's also a property called line, okay? So let me first go back to the scanner and try to rename here, refactor, rename, and call this guy line instead, okay? Now, if I go back to the parser, you see that it has now renamed line number over here to line, okay? But now what's really interesting is now I have two things called line, one coming from the scanner, and then I have one coming from this line call thing that I'm using in here as a local, right? Let's say that I now had to rename my scanner's line back to line number, okay? Now, if this was JavaScript code, that would be insanely hard to do, right? Because you have to look at every reference to line in all of your source files and decide on the fly, is this the one or is that another one? But this is what IDEs do for all day long, right? Because through static typing, we know the difference. So let me take this parser file here and actually put it down at the bottom. And now let's try to actually show both of them. Here you see the one in my scanner. Here you see the one that isn't related to it. Let's go back and say refactor, rename. And now let's call this guy line number instead. And you'll see that we renamed that guy, but not that guy, because we understand the difference between the two. So here we go. This is, again, one of those things that just make tooling incredibly valuable when you're writing large applications. Okay, final thing I wanted to show is just compiling the compiler. Sorry. There we go. So in here is the source for all of the compiler that we just took a look at. Now I'm going to try to compile the compiler. I'm going to tell it to put the output in a file called ts.js. Then I'm going to tell it to also generate declarations, and I'm going to compile TypeScript.ts. So this is going to produce two files. First, it's going to produce the compiler in a file called ts.js. And that's just going to be plain JavaScript. Then it's also going to produce a declaration file that represents the external interface of the compiler. So if we look at what we got here, you'll see that we had two files produced, ts.js and then ts.d.ts. And that's the declaration file for the compiler. And now if I load that one up in the development environment here, let's see, edit ts.d.ts. Here we go. And then let's just get rid of the parser. And here you see basically the public abstract of all of the things declared in the compiler that someone using the compiler as a service could use. And so now I can, in a sense, continue up the chain of my modular development. I can take my TypeScript compiler, run it through my minifier, do whatever it is that I do, my obfuscator before I ship it, and then I can continue on with the declaration file. And that really is what represents my external interface, right? And so you see how you can manually author declaration files for existing JavaScript, but if you're writing in TypeScript, we can make the declaration files for you automatically. All right. I think that is as much as I have time for. Wanted to just briefly summarize what's included in TypeScript. Open source compiler written in TypeScript itself. Tooling, there's a browser-hosted playground that uses these services, and because it's open source, anyone can build plugins to other editing environments. We built one for Visual Studio that we include. We include static typings of a bunch of the popular libraries out there, like Node.js and jQuery, and also lots of samples and a formal language specification. So, as I started out saying, application scale JavaScript development is hard. I hope I've showed you here how TypeScript makes it easier. And I'd love for you to go take a look at it yourself at typescriptland.org, download it, play with it, and let us know what you think. Thank you.